is gravitational fields. This is for Physics 12. We're starting out the new unit here. Going to be talking about sort of the note guide here. So essentially what I've got is I sent you guys this note guide here, and the unit consists of more or less 3 sections, okay? And it's gravitational fields, right? Kepler's laws, and gravitational potential energy, okay? The textbook explains those sections here, and you can do some extra practice questions in this location as well. All right, I'll probably go through the questions found in the note guide here, just several examples, right? I think I do gravitational fields first. Okay, that's this first several examples. Then I'll probably tomorrow I'll do gravitational potential energy. Okay, and then lastly I'll do Kepler's laws. Okay, and after we get through all of this stuff, there is some practice questions here. So here's more gravitational fields, some practice questions, a couple of solutions as well. Then there's gravitational potential energy here, and some practice questions, a couple of solutions. And then we've got Kepler's laws with a little bit of explanation and a couple of examples here as well with their accompanying solutions. Okay. And then we have just a wide range of questions that are mixed. It's not specifically broken into Kepler's laws or gravitational potential energy or gravitational fields per se. It's just a random mix of questions, and I think a lot of them have solutions. Some of them don't. I believe many of them do. There's a few that don't. So basically, yeah, kind of go through these. If you have any questions on these and you would like me to answer a specific question or something like that from this list, just let me know. We'll call this question 46 from the note guide, for example. If you don't understand something from this thing, we'll call this document the note guide. Otherwise, let's go all the way back up to the top here, scrolling way back up to the top. Otherwise, if you've got questions from the textbook that you'd like me to answer, we'll call these, textbook questions. So for example, let's say one of you has a question on the textbook, page 284, right? Number 3, for example. Okay. You can go ahead and formulate your questions like that. All right. And what I'd like for you guys to do, if you do have questions, here I'll show you. Here's the physics thing here. Go ahead and keep all of the gravitational field questions, if you could. Where is it? In this, or all the planetary motion questions in this little mini stream right here, right? And if there are questions, what I'll do is I'll kind of keep moving this over up to the top here, move to the top. And actually, I think it might automatically move to the top. Well, I'll move it to the top. All right. So there it goes. It's moved to the top. And now we can kind of answer these questions here. So let's say somebody has a question. It's be like, could you explain, the note guide number 15? And yeah, we would. That's how that would work. Okay, and you would say, question mark, and you would post it, and then I would underneath here, I would hopefully either answer the question if it's just a couple of words, or I would make a video and post the video in this location. Okay. That way, all the questions concerning planetary motion are in this little section. Okay. All right. So let's get to the note guide here. A gravitational field is in the space surrounding an object with mass, okay? And it is a property of each point in that space, okay? The strength of the field can be measured by combining Newton's second law and the law of universal gravitation, okay? And so our learning goal is the universal gravitation, to calculate the force of gravity, and to distinguish how to use the universal gravity formula. Okay. Now, let's go ahead and take a look at this first example question. The way that this note guide is set up, I ask several questions, and then as the questions unfold, we will get introduced to the new formula as they arrive, right? So calculate the magnitude of the gravitational field strength on the surface of the Earth and on the surface of Jupiter, okay? Well, as it turns out, the gravitational field strength is just a small g, which is a vector, okay? And it's equal to capital G m over r squared, okay? And this formula basically works such that m is the object that is producing the gravitational field, okay? R is how far you are from this object. And this thing here is a gravitational field, okay? Now, this gravitational field doesn't do anything until another mass enters its space, okay, where the field exists. If another mass enters it in, then that new mass experiences a force of gravity, okay? And so, therefore, then that arises the next formula. The force of gravity is G m over r squared times a new m, right? And basically you end up getting this older formula, which we're familiar with, all right? So basically what we're saying here is that the gravitational field, which is this thing, times a mass, which is that, should give me the force of gravity, okay? So you want to keep that in mind. The gravitational field is one formula, and then the force of gravity is another formula, okay? All right, so let's get on to answering this question. Calculate the magnitude of the gravitational field strength on the surface of the Earth, all right? So here we've got the Earth. There's some sort of object right there, and or there's nothing there. Maybe there's just some. Maybe it's me. I'm sitting there on Earth there, and I'm going to ask, what's the gravitational field strength? Well, it's going to just be capital G times capital M over R squared. Well, what are these values? Well, this is the mass of the Earth, and this is the distance from the center of the Earth. All of those values can be found on page 776 in your textbook. Maybe when you're taking the test, I believe I have most of these values written down in the questions. Otherwise, they're found on your formula sheet as well, some of these more common values. Matter of fact, I don't have them handy right now. I'm going to pause the video and grab my textbook really quickly. All right, so I'm looking here at the textbook, Table 6 on page 776. And, well, capital G is on the previous page, which is the universal gravitation constant. It's equal to 6.67 times 10 to the negative 11. And the units are Newton meter squared per kilogram squared. I won't write them down. It's just going to clutter up the page. Now I'm going to multiply that by the mass of the Earth. So that's on the next page. I don't have that one memorized. That would be 5.98 times 10 to the 24. So 5.98 times 10 to the 24. And then the distance from the center of the Earth to its surface, also called the radius of the object in that table. So 6.38 times 10 to the 6. 6.38 times 10 to the 6th, okay? And that is squared, all right? So basically what we're looking at here is we're just going to go ahead and take this, and I'm going to multiply all this through, all right? Now, when I multiply these guys through, I kind of, in my head, deal with these guys first, all right? So times 10 to the 6th squared is times 10 to the 12th. And times 10 to the 12th on the bottom cancels several of these on the top. And so this 24 minus 12 is going to be, 12, okay? And then I've got another negative 11 here. Oh, so it's actually, and then it's just going to be times 10. Look at that. It's going to be just times 10. All right. And so the result is 6.67 times 5.98 over 6.38, still squared, times 10 to the 1. Okay, and I've got no clue what those numbers add up, multiply. Actually, I do know what they do. It's the answer should be 9.8 here, but let's check it. I'm going to type this into my calculator just to make sure. Look at that. Sure enough, it was 9.79 or 9.8. Actually 9.799. I imagine it's actually more like 9.81. But I obviously didn't use some of these values. Whatever the case, that's the gravitational field strength on Earth. Okay? Now, the question also asks to figure out what's the gravitational field strength on Jupiter. So I'm going to go ahead and put a little E there, and then I'll put a little J right here. Okay? So that's Jupiter. And you're going to use the same formula, radius of Jupiter and mass of Jupiter, though, squared. And so it's just going to be 6.67 times 10 to the negative 11 times the distance from the center of Jupiter to its surface and the mass of Jupiter. Go into these little locations. I actually messed that up, but you see what I'm doing here. So I'm going to go ahead and write these down, getting them from table 6, and I will go ahead and zoom through all of this, and I'll pause the video and I'll get the solution here for you. And so I go ahead and wrote that in there. This is the mass of the Jupiter, 1.9 times 10 to the 27, and this is the distance from Jupiter. And it turns out after you calculate all this, you get around 25, okay? So we're just going to write down 25. And what's the units? This is newtons per kilogram, right? And the units here, so newtons per kilogram as well, okay? And what does that signify? That means every kilogram of mass should experience around 25 newtons of force downward on Jupiter, whereas on Earth, every kilogram should experience around 10 newtons of force, 9.8, okay? And that's what we're used to. Question now, example 2. How many times greater is the gravitational field of Jupiter than that of Earth? Well, this is pretty interesting. We actually already have this information. So this is like one of those how many times greater form things is, right? So if the question is asking you how many times greater is Jupiter than Earth, then what you're going to basically do is you're going to set up a ratio, gravitational field of Jupiter, gravitational field of Earth, and you're going to go ahead and put those now values. So this is 25, and this is 9.8, and the reduction of this, if you will go ahead and reduce this, you're going to get essentially the value, right? And so it's around 2.5 here, or 2.5, and it's times greater. Okay, there's a little E in here. There you go. Times greater. That's how you do one of those how many times greater formulas. How much larger or smaller would the gravitational field strength be for a spot that is 3 times further away from the center of any planet? Ah, interesting. Okay, so basically this is a how many times greater or smaller, right? For a spot that is 3 times further away from the center of any planet. So we've got 2 radii here. Let me draw a picture, actually, for this one. I've got some theoretical planet, and we're right here. And we've got the gravitational field strength. We'll call that G. Now I go 3 times further away, right? So this is 1, right? This is 2, and this is 3. So that would be over here, 3 times away. And so now I've got this gravitational field strength here as well. All right. I'll call this gravitational field strength 1, and I'll call that one 2. All right. Well, gravitational field strength 1 has a radius, which I'll just call R1. I'll call this one R2. All right. So basically, I want to know how many times further would gravitational field strength, how many times larger or smaller would G2 be than G1? Okay. Well, let's go ahead and put these values in here. Well, we would write their numbers, right? For example, up here, we wrote 25 and 9.8. Okay. Up here, 25 and 9.8. So we would write our numbers. Here's the number and here's the number. But wait, we don't have the numbers. Oh, shoot. What are we going to do? Well, where did these numbers come from? 25 and 9.8. Let's go back up. Well, if we go back up a little bit, we see, oh, wait, these numbers came from this formula. All right. So instead of writing the numbers, since we don't know the number, let's just go ahead and write the actual formula. All right. So if we write the formula here, it's going to be G, mass of the planet, over radius 2 squared, and G, mass of the planet, over radius 1 squared. Okay, and that line is a little long, so I'll make it a little bit shorter. Now, if I go ahead and do some algebra here, I've got basically a fraction divided by a fraction. Okay, and that's basically going to be G, mass of the planet, over R2 squared times R1 squared over G times mass of the planet. Because remember, when you divide by a fraction, you multiply by its reciprocal. Oh, but look at this. This is spectacular. G actually just cancels with G. Wait, mass of the planet is the same in both cases. So this is actually just going to end up being R1 squared over R2 squared, right? But wait a minute, what's the relationship between R1 and R2? Well, it turns out that R2 is equal to 3 times R1. You see that? R2 is this, which is 3 times larger than R1. Look at that. So now that I know that this is true, I'm going to go ahead and place, instead of R2 here, I'm going to replace R2 with 3 times R1. So this is R1 squared over R2 squared, which is just 3R1. And I'll go ahead and move out this way here. Maybe we can even go in a little bit here. So let's say, oh, look at this. Now I got R1 squared over 9R1 squared. And it looks like I'm getting 1 over 9. All right. So that's going to be our final result there. How many times larger or smaller is the, let's go ahead and sort of recap that. So G2, the field strength divided by G1 is 1 over 9, meaning that G2 is 1/9 the amount of G1, all right? And that's what we're looking at. All right. Those are some questions that you were going to be talking about there. Now, let's combine the equations for circular motion with the above. Learning goal. Discover the origin of the orbital velocity formula. Success criteria. Discuss how the orbital velocity is derived from the centripetal acceleration formula. Interesting. Okay, so now let's combine the equations for circular motion with the above equation. Oh, look at that. The above equation. The above equation I'm talking about would be this one, right? Well, either one of these, actually. Let's go with this one. Let's take the gravitational field strength, all right, formula, which is G. I don't like that color. Let's go with, let's switch with the R. G is, there we go. Oh, going wild here. There you go. Okay. Is going to be G M R squared. Right? That's the acceleration of gravity. All right? And let's go ahead and draw like a theoretical planet. Now, if I'm in orbit around this planet, what's going to happen is I've got some sort of circular motion going on, right? So let's go back to Unit 3. Remember that this is the formula for circular motion. It got quite messed up in my transferring of documents here. And so this is, I'll go ahead and rewrite this for us. Centripetal acceleration is equal to V squared over R, right? And so that's this section here. That's what that's supposed to be. I must have gotten all messed up. So I'll fix that. Hopefully you can fix that on your copy if it's messed up. I've been doing some cutting and pasting here, so things got all wild. Turns out that my gravitational field strength in orbit is equal to my centripetal acceleration. Okay? Oh, but wait, my centripetal acceleration is equal to V squared over R. And so if I basically take this formula here and this formula there, and I now set them equal to each other, I'm basically dealing with the following. V squared over R equals G M over R squared. Okay? Oh, just got an email. Let me pause this. I'll be right back with you guys. Hello? Okay, so we're back again. Basically, what we're looking at is we're trying to figure out the orbital velocity now, okay? And this red formula that I've got going on right here, this V is the velocity with which the object has as it moves around this circular path, right? So that's a little velocity vector going there, okay? And that's this little V, right? And so basically, if we simplify for this value, we get V equals capital G M R over R squared. And that's going to be squared still. And now, essentially, look, this R cancels with one of those. And so the actual formula is going to be V equals GM over R, okay, rooted. What is this formula going to do for you? Basically, if the question is talking about some physics question in this unit, it's talking about an object that is in orbit, right? It is orbiting some planet or some moon or some satellite or something like that. If it's successfully orbiting, okay, you can use this formula here to determine the speed at which it orbits based on the distance from the planet, okay? The distance from the planet's center, not the planet's surface. And this is the mass of the central object, okay? It's not the mass of the orbiting object, all right? And so we're going to use the above equation to find the required velocity for a satellite of height 3 Earth radiuses above its surface. So now, in order for an object to successfully orbit at the height of 3 Earth radii. So that would be the number 3 keeps showing up here. Boom, boom, above the surface. Okay. So that's 3 radii above the surface itself. If I want to actually successfully orbit the Earth at this location, I need to have this velocity, the orbital velocity. It's actually kind of nice. And so let's go ahead and plug this in here. Let me go. The velocity that I need is equal to the square root of g times m over how far I am from the central object. But the m is actually equal to Earth, right? This is the Earth's mass, all right? And the Earth's mass, if I remember correctly, is something like 20 something, 24, yeah, 5 times 9, 5.98 times 10 to the 24 goes there. And then this is basically the distance from the center of Earth. Don't forget this. So that's going to be 4 Earth radii here. And the radii for an Earth, again, is 6.38 times 10 to the 6.38 times 10 to the 6th, okay? And that is going to be my orbital velocity, right? And then obviously this g is going to be 6.98 or something like that times 10 to the negative 11, 6.67, I think it is. Is it 6.67 times 10 to the negative 11? And you kind of calculate all of this stuff. I won't necessarily go through that calculation. Actually, I will. I'll go through that calculation. Let me pause the video. I'll get right back to you. All right, so I went ahead and just calculated that out, and I got around 4,000 meters per second. It's pretty fast. Yeah, I got an answer that was huge. I was like, oh man, I must have done something wrong here. And then I forgot that I actually needed to square root this because I didn't write my square root there. So I think I ended up getting like, whoa, giant number. You know what I mean? So that was crazy. I was thinking, that's like faster than the speed of light. This isn't right. And so, yeah, just don't forget that was supposed to be square rooted. All right. There you have it. That's the gravitational introduction to some of those formulas, right? And so the 3 formulas that we learned there were the orbital velocity formula, the gravitational field strength formula, and then the force of gravity formula as well, which is an older formula that you're a little bit more familiar with. Don't forget that you can actually have the orbital period here and the orbital frequency here. I'll do a little bonus scenario. Let's say I've got, I want to figure out the orbital period. Don't forget that the acceleration, centripetal, is equal to the gravitational field strength if you are in orbit. This is in a successful orbit. Okay, orbit meaning circle, boom, circular motion, right? Now, they say this is an estimation because things actually tend to orbit in an ellipse, all right? But for our purposes, we're in this course, we're going to make the assumption that these ellipse shapes orbits are more or less circular, okay? And we're going to be getting more average values in these cases, okay? So under those circumstances, remember the centripetal acceleration is 4 pi squared r over t squared, and the gravitational field strength is g m over r squared. Boom, look at that. And now I can basically figure out for the orbital period here. Orbital period is going to be this value right there, okay? Now I just solve for period. So I guess I could pass the period up like this, So I'm going to get t squared. I'm going to keep my 4 pi squared, my g and my m. I'm going to get an r to the third over here. And then I've got everything square rooted. And boom, erase that square root. This is going to be your orbital period at a certain distance, r, from a object mass m. Okay, and the mass of the orbiting object doesn't show up here. It's only the mass of the object that is in the center, that everything orbits around, shows up. So that's another thing you want to keep in mind here, right? So we've got our orbital velocity formula and our orbital period formula. That is going to be pretty cool there. Hopefully I went through this really quickly. Hopefully I didn't make any mistakes. If I did, let me know in the somewhere in the chat. Uh, um, anyway, I'll post this up in a few minutes.